All right, so in this section, we're going to look at quadratic systems. Now, remember, we talked about systems of linear equations. Now we're going to do quadratic systems. So when we learned about systems of linear equations, we looked at two lines, and we talked about what happens when we graph these two lines on the same coordinate plane. So there was three possibilities. When you graph them, they can intersect at one point, so we have one solution. They can intersect at every point, which means they are the exact same lines, which is infinitely many solutions, or they could never intersect, so they are parallel lines. And remember, we had many methods to solve these. We did elimination, substitution, and graphing. So whenever we did elimination or substitution, infinitely many solutions means I got an answer that looked like this: 0 equals 0 or 1 equals 1, just some true statement. And no solution looked like something that didn't make sense, like 7 equals 2, something that was never true. And one solution, we had one x and y coordinate where they intersected. Now, a system of quadratics looks a little bit different. Now, we're going to be looking at many types of systems of quadratics. Here is an example of a line with a parabola, okay? So there's different situations that can happen. I can have two solutions where the line cuts through the parabola twice. I can have one solution where the line just intersects right at the vertex, or I could have no solution where they never intersect. Now, we're also going to be looking at systems that have absolute value, that have two parabolas. So there's going to be different situations, but these are the three outcomes: two solutions, one solution, no solution. So for two solutions, that means there's going to be two pairs of points, x and y, that work. One solution, just one pair, and no solution, no pair. So you'll get something that maybe doesn't make sense, like when you solve like 7 equals 2 or something like that. So one method of solving this is by graphing. So we're going to go ahead and we're going to graph these two. I'm going to graph the line in orange. So remember, to graph a line, you start with your b, right? Y equals mx plus b. So I go ahead and plot my y-intercept, which is 3. And then I'm going to use my slope here, which is the coefficient of x, which is going to be 1 in this case. And I'm going to use my slope to move from b. So I'm going to go up 1 over 1, up 1 over 1, right? Rise over run. I can also go down 1 over 1, down 1 over 1. Okay. And then once I feel like I have enough points to create a straight line, I go ahead and create my straight line. I'm going to label, here's my y-intercept, which is 0, 3. My x-intercept is negative 3, 0. Okay, and that's the line y equals x plus 3. Now I'm going to go ahead and graph the parabola. Remember, there's a few more steps I have to do for this. So I have to do negative b over 2a to find my vertex. So that's negative 6 over 2 times 1. So that's negative 3. So the y-coordinate of my vertex is negative 3. Go ahead and plug in negative 3 into my function to get my y-coordinate. So 9 minus 18 plus 9, that's negative 9 plus 9, which is 0. So the y-coordinate of my vertex is 0. So I'm going to start right here, okay, which hopefully you already see the intersection point. So that's the vertex, but I still need to graph my parabola. So I'm going to pick points close to negative 3, so let's pick negative 2. When I plug in negative 2, I get positive 1, so I'm going to go ahead and graph that. Negative 2, positive 1. Let's go ahead and plug in negative 1. I get positive 4, so negative 1, 4. And remember, here's my AOS. So I'm going to reflect over my AOS to get my other points. I'm going to go ahead and graph this parabola. Okay, so hopefully you see here that the intersection points are pretty obvious. My solutions here are going to be these values. They intersect here and they intersect here. Okay, so my solution to this problem would be negative 3, 0 and negative 2, 1. Those are the two solutions to the system. Now, since they're solutions, you can take negative 3, plug it into each one, and you should get 0 for y. You should be able to take negative 2, plug it in for x, and get y equals 1. So solving by substitution is also a method that I can use if I would like to not have to graph. So remember, we did substitution when we did systems of equations. Whenever I have a variable that's already solved for, I can look for that same variable in the other equation, and I can replace that variable with whatever the other one equals. So here, y equals x plus 3. So everywhere I see a y, I'm going to replace it with x plus 3. So I'm going to have x plus 3 equals x squared plus 6x plus 9. And now I just have to solve for x. So hopefully we are comfortable with solving with quadratics. So I'm going to go ahead and combine like terms, or bring everybody on the same side. So 3 equals x squared plus 5x plus 9. Go ahead and bring the 3 over. 0 equals x squared plus 5x plus 6. Remember, we have to be equal to 0 to solve a quadratic. So I'm going to go ahead. This guy looks pretty factorable. Now you could use the quadratic formula. You could complete the square. But if it's factorable, that's the easiest method. So factors of 6 are 6 and 1 and 2 and 3. So x and x, 2 and 3, same, both positive. So solving this, it's going to be x equals negative 2 or x equals negative 3. So now that I have my x coordinates, that means with my solutions up here, I know my x coordinates, negative 2, negative 3. I need the y coordinates. Well, how am I going to find those? Well, just like we used to do, how did you find y? You plugged it back in, right? So now I'm going to go ahead and plug back in. Now, remember, it doesn't matter which original you plug back into. Well, obviously, it's easier to plug back into the linear one than the quadratic. You're going to make less mistakes. So y equals, I'm plugging in for x here, negative 2 plus 3, which gives me positive 1. Y equals negative 3 plus 3, which gives me 0. So my two solutions here are negative 2, 1 or negative 3, 0. Now remember, you should still check your answer. Take these two values, take negative 2, plug it in for x. You should get 1 in both equations. Take negative 3, plug it in for x, and you should get 0 for both equations. On the slide before this, we graphed to solve, and notice that we got the same answer regardless of the method that we used. We got the same answer when we graphed. Okay, here's another example of substitution. So these are already both solved for y, which means you just set them equal to each other. So negative x squared plus 5 equals x squared minus 4x plus 5. I'm going to go ahead and start solving. So I'm going to bring everything to the same side. So I'm going to add x squared to both sides. 5 equals, well, combining these like terms, I have 2 x squareds. Bring the 5 over. 0 equals 2x squared. These guys go away, minus 4x. Hopefully you remember how to solve this type of equation. This guy, I could use quadratic or completing the square, but he's factorable, so I'm going to go ahead and factor it. I'm going to take out a 2x. I'm left with x minus 2, right? Double check, do your math. 2x times x is 2x squared. 2x times negative 2 is negative 4x, so I did it right. I set each of these equal to 0. So I'm going to get x equals 0 or x equals positive 2. So as far as my solutions go, I have the x coordinates. I have 0 and 2. I need the y coordinates. So I'm going to go ahead and plug in. Doesn't matter which equation I plug into. This one looks like maybe you guys might get tripped up by the negative, but that one should be easier because it has less places to plug in. So plugging in 0, I get y equals negative 0 squared. Notice the parentheses that I just drew because that negative is on the outside of what I'm plugging in. So that's y equals 0 plus 5, which is just 5. So whenever x is 0, y is 5. And when I plug in 2, y equals negative, notice the parentheses there, plus 5. So that's going to give me negative 4 plus 5, which is 1. So my two solutions are 0, 5, or 2, 1. Go ahead, plug these back into both, and they should work in both. Okay. Okay, so here I have a system that is absolute value and a line, so a little bit different, but still a system that I can solve by graphing. So I'm going to go ahead and graph each line and see where they intersect. So recall for absolute value, I still have a vertex, HK. It's just like our parabolas whenever our parabolas are in vertex form. So this minus here actually means positive. So I'm going to go over 2, 1. That's my vertex, 2, 1. And then because there's nothing in front of the absolute value bar, there's nothing in front of x, my slope is 1 here on both directions. Remember, absolute value should have a v. So go ahead and graph that. I'm going to go ahead and write the y-intercept, which is 0, 3. All right, now I'm going to graph this line here. This line has a slope of positive 1/3 and its y-intercept is negative 2. So I'm going to go down to negative 2. Slope of positive 1/3 means I rise 1, run 3. Rise 1, run 3. Rise 1, run 3. Or fall 1, run 3. Okay, and I go ahead and graph that. Okay, so where are my solutions? Do they intersect? No, they don't intersect. So my solution is no solution. Remember, we are looking for the intersection points, but they never intersect, so there's no solution. And of course, if this was a graph that you were turning into me, you would want to label everything. You wouldn't want to do what I just did. You want to have everything labeled, have your line labeled, and your absolute value function labeled, along with total 5 points. So just label a few more points on each graph. I'll go ahead and label this guy. Alright, so go ahead and try these on your own. A few of them have graphs, so I will be checking those graphs in class, but you can put your solutions in your Google form. So please make sure you try your best, try all of them, and then we will go over them in class.